Hey, hello guys, welcome to my YouTube channel. In this video, we are going to learn how to use the solution series method to solve differential equations, part 2. The differential equation we are interested in is given in this form. Okay, so this is the second order differential equation, and our aim is to solve this particular differential equation. So to start, we assume that this differential equation has a solution of this form. So where our y is equal to the summation of a subscript n x raised to power r plus n, and the idea is for us to determine the values of a subscript n and r. Once we know those parameters, then we can substitute it back into this equation, and that's all. So as usual, the expansion of this expression of this equation is giving us this, where this one is a naught x r then n when it is 0, when it is 1, when it is 2, and when it is 3 down to infinity. So once we know a naught, a subscript 1, a subscript 2, a subscript 3, and also the value of r, then we are done. Okay, so the next thing we do is to differentiate this expression with respect to x once because of this dy dx, and that gives us y prime. Our y prime here represents dy dx once, which is given out by this. So if you differentiate this one with respect to x, our r plus n comes back, leaving r plus n minus 1, which is this. So it's also important for us to differentiate it the second time, which will give us y prime prime, and that gives us this expression. Okay, so with this equation, and this equation, we can substitute those three equations into this particular expression, and we have something of this form. So we see the first part, which is the y prime prime, second part, which is y prime, then the last part, which is just y equal to 0. Okay, so we can send this 4x in and simplify this part, send this 2 in and simplify, and let's see what happens. Okay, so with this, x goes into these parts, reducing this one by 1, then 4 comes here, 2 goes in without doing nothing, then without doing nothing. So what you notice is that this expression here and this expression here, they are the same family, they are the same. So we can factorize, and this equation will reduce to this expression here. So we can see we have our an, I brought it forward, then xn plus r plus n minus 1 is here. So we have r plus n minus 1, then this 4 here, then plus 2 r plus n, then with this expression, which is this one here. So from here we can simplify this one in whatever method way you wish to, but what I'm going to do is to factorize this one and this out, and let's see what our expression, the next expression, will look like. So after factorizing this one and sending 4 into these parts, you notice that this 4 goes into r, 4 goes into n, 4 goes into this. Now when you factorize this out, you'll be left with this one plus 2. So this 4 times 1 will give us minus 4 plus this 2 that is left here, which is what? Minus 2, right? Then we have this expression and this. Okay, so from here, the next thing is to see how we can get our initial equation. And to get our initial equation, we concentrate on these parts here, and wherever we see n, we set n equal to 0. And in so doing, let's see what goes to the next line. Okay, so n becomes 0. In this case, n becomes 0. In this case, n becomes 0. Then in this case, n becomes 0. And if you simplify further, it will reduce to this. So we have a naught, ordinary r remaining, then 4r minus 2 here, then xr plus 0 minus r minus 1 will be here. Okay, so but if you look at this expression, compare this power with the previous power of the series, you discover this particular one is not in the series. So let's take a look. Right, so in that case, then because it is not, then the coefficients of x raised power r minus 1 will be 0. So that's why a naught times r, and this must be 0. If we go back, you'll notice that this expression, this power r minus 1 is not in the previous series expansion. So because it's not there, the coefficients of this expression will become 0. So that's why this part is here is equal to 0. And if we factorize 2 out, that 2 can go away. You will be left with the next one here, which is this. Okay, now because our a naught cannot be equal to 0, why is it so? Because it's one of the important parameter in this series, and other values of a subscript 1, 2 can be dependent on this one. So this one can never be 0. And if that's the case, then r times this must be the one that will be equal to 0. So we have that it's either r equal to 0 or r equal to what? Half. And if that's the case, we recall this expression back, and we use this part again, still this part and this part, to get our recurrent relation. To get our recurrent relation, we need to do something to this to make it look like this one here. And to do something here, what we need to do is to add, wherever we see n, we replace with n plus 1, and it will reduce to this. Wherever we see n here, replace with n plus 1. Wherever I see n here, replace with n plus 1. Wherever I see n here, replace with n plus 1. And that gives us this part here. So we've seen n plus 1, n plus 1, then 2, n. So you notice that this part is now this one, which looks exactly like this one. So from here, we can factorize our x, r plus n out, and that leads to okay, we can even resimplify this one, which is 4r, 4n plus 4, 4 minus 2 will give us 2, which is equal to this one. Then we can easily factorize these 2 out, and let's see what happens. Okay, so we took care of the summation sign first, then this and this we can factorize and send it to 0. Then we are left with this part plus this part, that's this one and this one, this part and this part. When you factorize, you take care of it. Okay, so from here we can send this one to this other side, and that gives us this. Then making a subscript n plus 1 the Sevier formula, it simply means divide everything by this, and that gives us this expression. And from these points, you will notice that we have already found out that our r is either 0 or half. So let's write down the expression. Let's reduce this expression to those two possible scenarios for r equal to 0 and r equal to half. So we have this. So this expression reduces to this for r equal to 0. If you see r is 0, you have n plus 1. For r is 0, you have 4n plus 2. Then for r equal to half, you have half plus 1 will give us 3 over 2 plus n, which is this one. Then if you have half here, half of 4 will give us 2, 2 plus 2 will give us 4. So we have these two scenarios. So first of all, let's concentrate on this part and find the other terms, higher terms of a. Then we'll keep that one, then find the higher terms of a for this one and add the two solutions together. Okay, so we'll start with this one by putting 0 here. And if you put 0 here, you put 0, put 0, then you put 0. So here will become a1 equal to minus a0. So let's see. So this is what we have. So a1 equal to minus a0. If you put 0 here, it becomes 1. If you put 0 here, it becomes 2. So we can do for a1 and a2. And let's see what our result will be. So when here is 2, it means here is 1. Here is 1. When here is 1, here becomes 2. When here is 1, it becomes 4 plus 2, which is 6. And 6 can be split into 2 times 3, which is 6, leaving a1 here. but we have already found the value for a1, which is this expression. So if I replace now, minus a naught 1 over 2, which is this part. So 1 all over this, minus 1 all over this part is here, then minus a naught all over 2 is here, which can be simplified as a naught, because these two will cancel out. You have 2 2 3 2 2 2 2 3. Okay, so that's that for. So if you recall the expression for our y, which is all these parts, and we have established that our r is 0 for the first possible solution, then we can substitute the value of a naught that we have found, the value of a1, value of a2, and that goes to these points. So a naught x raised by 0 plus 0 will give me 1. We have 1 here. a1 is minus a naught x all over 2. Then this is my x, because here is 0. X 0 plus 1 becomes x. Our a1 is 2 if you check. Likewise, this one, a2 is this multiplied by this one. a3 is this multiplied by this. When you check those ones, so at the end of the day, we can factorize a naught out and convert this one to factorials, and that leads to a naught leaving 1 behind minus x alone all over 2 factorial, x squared all over 4 factorial, and x cubed all over 6 factorial. Hence we can easily predict what will be the next value, right? So this is the first solution. Let's go to the second solution. So we start with this one again and substitute the value of 0 0 0 0, and let's see what happens to get our a1. a1 becomes minus a naught, here is 0, 3 over 2, here is 0, here is 4. So 2 will take care of 4, giving us 2. So this is for a1. We can also use the same method for a2. So if I put 1 here and I put 1 here, it becomes a2, which is this. Here comes a1. If I put 1 here, 1 plus 3 over 2 will give me what? 5 over 2. Then 4 plus 4 will give me 8. 2 takes care of this, leaving it as 4. So we have 4 and 5 for the first part. But already we found the value of a1, which is minus a naught 3.2. So minus a naught 3.2. If you simplify this, gives a naught all over 5 factorial. So we can even do for a3, right? You can check it out. Then finally we substitute the expression into this y2, which is these expressions. Remember, our r here for y2 is half, so that's why we have half. 1 here is 0. Half plus 1 will give me 3 over 2. Half plus 2 will give me 5 over 2, and so on and so forth. So when you substitute this one into this, see what we get. Okay, so for the first 3 terms, that's all we need. y2 becomes a naught x this minus a naught x 3 over 2 over 3 factorial. Likewise this. Or you notice a naught is common, so we can factorize out. Even a naught x raised by half is common, leaving 1 minus. If you remove x half from here, you are left with 1. If you remove half from here, you are left with 2 as x raised by 2. So at the end of the day, then we can resimplify further by converting this one to square root of x, and we have 1 minus x 3 factorial plus this factorial. So if this is a y2, then the solution to the original equation will now be the summation of y1 and y2. So we have this y equal to y1 plus y2, which is equal to this expression plus this expression. And that's all. If you look at this expression, it might not look like one of these special type of series, so you can just leave it that way. I hope this helps. Please like, share and subscribe to the channel. Thank you.